Part 2, Chapter 2 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 2, Solar Observations and Theories, Part 1. The zeal with which solar studies have been pursued during the last half-century has already gone far to redeem the neglect of the two preceding ones. Since Schwab's discovery was published in 1851, observers have multiplied, new facts have been rapidly accumulated, and the previous comparative quiescence of thought on the great subject of the constitution of the sun has been replaced by a bewildering variety of speculations, conjectures, and more or less justifiable inferences. It is satisfactory to find this novel impulse not only shared, but to a large extent guided by our countrymen. William Rudder Dawes, one of many clergymen eminent in astronomy, observed in 1852, with the help of a solar eyepiece of his own devising, some curious details of spot structure. The umbra, heretofore taken for the darkest part of the spot, was seen to be suffused with a mottled nebulous illumination, in marked contrast with the striated appearance of the penumbra, while through this cloudy stratum a black opening permitted the eye to divine farther unfathomable depths beyond. The whole, thus disclosed, evidently the true nucleus, was found to be present in all considerable as well as in many small maculae. Again, the whirling motions of some of these objects were noticed by him. The remarkable form of one, sketched at Wateringbury in Kent, January 17, 1852, gave him the means of detecting and measuring a rotatory movement of the whole spot round the black nucleus at the rate of 100 degrees in 6 days. It appeared, he said, as if some prodigious ascending force of a whirlwind character, in bursting through the cloudy stratum and the two higher and luminous strata, had given to the whole a movement resembling its own. An interpretation founded, as is easily seen, on the Herschelian theory, then still in full credit. An instance of the same kind was observed by Mr. W. R. Burt in 1860, and cyclonic movements are now a recognized feature of sun-spots. They are, however, as Father Secchi concluded from his long experience, but temporary and casual. Scarcely 3% of all spots visible exhibit the spiral structure which should invariably result if a conflict of opposing or the friction of unequal currents were essential and not merely incidental to their origin. A whirlpool phase not unfrequently accompanies their formation, and may be renewed at periods of recrudescence or dissolution, but it is both partial and inconstant, sometimes affecting only one side of a spot, sometimes slackening gradually its movement in one direction to resume it, after a brief pause, in the opposite. Persistent and uniform motions, such as the analogy of terrestrial storms would absolutely require, are not to be found, so that the cyclonic theory of sun-spots, suggested by Herschel in 1847 and urged from a different point of view by Faye in 1872, may be said to have completely broken down. The drift of spots over the sun's surface was first systematically investigated by Carrington, a self-constituted astronomer gifted with the courage and the instinct of thoughtful labour. Born at Chelsea in May 1826, Richard Christopher Carrington entered Trinity College, Cambridge, in 1844. He was intended for the Church, but Professor Challis's lectures diverted him to astronomy, and he resolved, as soon as he had taken his degree, to prepare with all possible diligence to follow his new vocation. His father, who was a brewer on a large scale at Brentford, offered no opposition. Ample means were at his disposal. Nevertheless, he chose to serve an apprenticeship of 3 years as observer in the University of Durham, as though his sole object had been to earn a livelihood. He quitted the post only when he found that its restricted opportunities offered no farther prospect of self-improvement. He now built an observatory of his own at Redhill in Surrey, with the design of completing Bessel's and Argelander's survey of the northern heavens by adding to it the circumpolar stars omitted from their view. This project, successfully carried out between 1854 and 1857, had another and still larger one superposed upon it before it had even begun to be executed. In 1852, while the Redhill Observatory was in course of erection, the discovery of the coincidence between the sun-spot and magnetic periods was announced. Carrington was profoundly interested, and devoted his enforced leisure to the examination of records, both written and depicted, of past solar observations. Struck with their fragmentary and inconsistent character, he resolved to appropriate, as he said, by close and methodical research, the 11-year period next ensuing. He calculated rightly that he should have the field pretty nearly to himself, for many reasons conspired to make public observatories slow in taking up new subjects, and amateurs with freedom to choose and means to treat them effectually were scarcer then than they are now. The execution of this laborious task was commenced November 9, 1853. It was intended to be merely a paragon, a second subject upon which daylight energies might be spent, while the hours of night were reserved for cataloguing those stars that are bereft of the baths of ocean. Its results, however, proved of the highest interest, although the vicissitudes of life barred the completion in its full integrity of the original design. By the death in 1858 of the elder Carrington, the charge of the brewery devolved upon his son, and eventually absorbed so much of his care that it was found advisable to bring the solar observations to a premature close on March 24, 1861. His scientific life may be said to have closed with them. Attacked 4 years later with severe and, in its results, permanent illness, he disposed of the Brentwood business and withdrew to Churt, near Farnham in Surrey. There, in a lonely spot on the top of a detached conical hill known as the Devil's Jump, he built a second observatory, and erected an instrument which he was no longer able to use with pristine effectiveness. And there, November 27, 1875, he died of the rupture of a blood vessel on the brain before he had completed his 50th year. His observations of sun-spots were of a geometrical character. They concerned positions and movements, leaving out of sight physical peculiarities. Indeed, the prudence with which he limited his task to what came strictly within the range of his powers to accomplish was one of Carrington's most valuable qualities. The method of his observations, moreover, was chosen with the same practical sagacity as their objects. As early as 1847, Sir John Herschel had recommended the daily self-registration of sun-spots, and he enforced the suggestion with more immediate prospect of success in 1854. The art of celestial photography, however, was even then in a purely tentative stage, and Carrington wisely resolved to waste no time on dubious experiments, but employ the means of registration and measurement actually at his command. These were very simple, yet very effective. To the helioscope employed by Father Scheiner 2 centuries and a quarter earlier, a species of micrometer was added. The image of the sun was projected upon a screen by means of a firmly clamped telescope, in the focus of which were placed 2 cross wires, forming angles of 45 degrees with the meridian. The 6 instants were then carefully noted, at which these were met by the edges of the disk as it traversed the screen, and by the nucleus of the spot to be measured. A short process of calculation then gave the exact position of the spot as referred to the sun's centre. From a series of 5,290 observations made in this way, together with a great number of accurate drawings, Carrington derived conclusions of great importance on each of the 3 points which he had proposed to himself to investigate. These were the law of the sun's rotation, the existence and direction of systematic currents, and the distribution of spots on the solar surface. Grave discrepancies were early perceived to exist between determinations of the sun's rotation by different observers. Galileo, with comfortable generality, estimated the period at about a lunar month; Scheiner at 27 days; Cassini in 1678 made it 25.58. Delambre in 1775 no more than 25 days. Later inquiries brought these divergences within no more tolerable limits. Langier's result of 25.34 days, obtained in 1841, enjoyed the highest credit, yet it differed widely in one direction from that of Böhm, 1852, giving 25.52 days, and in the other from that of Ctesias, 1846, giving 25.09 days. Now the cause of these variations was really obvious from the first, although for a long time strangely overlooked. Scheiner pointed out in 1630 that different spots gave different periods, adding the significant remark that one at a distance from the solar equator revolved more slowly than those nearer to it. But the hint was wasted. For upwards of 2 centuries, ideas on the subject were either retrograde or stationary. What were called the proper motions of spots were, however, recognized by Schroeter, and utterly baffled Langier, who despaired of obtaining any concordant result as to the sun's rotation except by taking the mean of a number of discordant ones. At last, in 1855, a valuable course of observations made at Capo di Monte, Naples, in 1845-6, enabled C. H. F. Peters to set in the clearest light the insecurity of determinations based on the assumption of fixity in objects plainly affected by movements uncertain both in amount and direction. Such was the state of affairs when Carrington entered upon his task. Everything was in confusion. The most that could be said was that the confusion had come to be distinctly admitted and referred to its true source. What he discovered was this, that the sun, or at least the outer shell of the sun, visible to us, has no single period of rotation, but drifts round, carrying the spots with it at a rate continually accelerated from the poles to the equator. In other words, the time of axial revolution is shortest at the equator and lengthens with increase of latitude. Carrington devised a mathematical formula by which the rate or law of this lengthening was conveniently expressed, but it was a purely empirical one. It was a concise statement, but implied no physical interpretation. It summarized, but did not explain, the facts. An assumed mean period for the solar rotation of 25.38 days, 25 days 9 hours, very nearly, was thus found to be actually conformed to only in 2 parallels of solar latitude, 14 degrees north and south, while the equatorial period was slightly less than 25, and that of latitude 50 degrees rose to 27 days and a half. These curious results gave quite a new direction to ideas on solar physics. The other 2 elements of the sun's rotation were also ascertained by Carrington with hitherto unattained precision. He fixed the inclination of its axis to the ecliptic at 82 degrees 45 minutes, the longitude of the ascending node at 73 degrees 40 minutes, for the epoch 1850 A.D. These data, which have scarcely yet been improved upon, suffice to determine the position in space of the sun's equator. Its north pole is directed towards a star in the coils of the Dragon, midway between Vega and the pole star. Its plane intersects that of the earth's orbit in such a way that our planet finds itself in the same level on or about the 3rd of June and the 5th of December, when any spots visible on the disk cross it in apparently straight lines. At other times the paths pursued by them seem curved downward to an observer in the northern hemisphere between June and December, upward between December and June. A singular peculiarity in the distribution of sun-spots emerged from Carrington's studies at the time of the minimum of 1856. Two broad belts of the solar surface, as we have seen, are frequented by them, of which the limits may be put at 6 degrees and 35 degrees of north and south latitude. Individual equatorial spots are not uncommon, but nearer to the poles than 35 degrees they are a rare exception. Carrington observed, as an extreme instance, in July 1858, one in south latitude 44 degrees, and Peters in June 1846 watched during several days a spot in 50 degrees 24 minutes north latitude. But beyond this no true macula has ever been seen, for Lahir's reported observation of one in latitude 70 degrees is now believed to have had its place on the solar globe erroneously assigned, and the veiled spots described by Trouvelot in 1875 as occurring within 10 degrees of the pole can only be regarded as, at the most, the same kind of disturbance in an undeveloped form. But the novelty of Carrington's observations consisted in the detection of certain changes in distribution concurrent with the progress of the 11-year period. As the minimum approached, the spot zones contracted towards the equator, and there finally vanished. Then, as if by a fresh impulse, spots suddenly reappeared in high latitude, and spread downwards with the development of the new phase of activity. Scarcely had this remark been made public when Wolf found a confirmation of its general truth in Böhm's observations during the years 1833 to 36, and a perfectly similar behavior was noted both by Spörer and Secchi at the minimum epoch of 1867. The ensuing period gave corresponding indications, and it may now be looked upon as established that the spot zones close in towards the equator with the advance of each cycle, their activity culminating, as a rule, in a mean latitude of about 16 degrees, and expiring when it is reduced to 6 degrees. Before this happens, however, a completely new disturbance will have manifested itself some 35 degrees north and south of the equator, and will have begun to travel over the same course as its predecessor. Each series of sunspots is thus to some extent overlapped by the succeeding one, so that while the average interval from one maximum to the next is 11 years, the period of each distinct wave of agitation is 12 or 14. Curious evidence of the retarded character of the maximum of 1883 4 was to be found in the unusually low latitude of the spot zones when it occurred, their movement downward having gone on regularly while the crisis was postponed. Its final symptoms were hence displaced locally as well as in time. The law of zones was duly obeyed at the minima of 1890 and 1901, and Spörer found evidence of conformity to it so far back as 1619. His researches, however, also showed that it was in abeyance during some 70 years previously to 1716, during which period sun-spots remained persistently scarce, and auroral displays were feeble and infrequent even in high northern latitudes. An unaccountable suspension of solar activity is, in fact, indicated. Gustav Spörer, born at Berlin in 1822, began to observe sunspots with the view of assigning the law of solar rotation in December 1860. His assiduity and success with limited means attracted attention, and a government endowment was procured for his little solar observatory at Anklam in Pomerania, the Crown Prince, afterwards Emperor Frederick, adding a 5-inch refractor to its modest equipment. Unaware of Carrington's discovery, not made known until January 1859, he arrived at and published in June 1861 a similar conclusion as to the equatorial quickening of the sun's movement on its axis. Appointed observer in the new astrophysical establishment at Potsdam in 1874, he continued his sun-spot determinations there for 20 years and died July 7, 1895. The time had now evidently come for a fundamental revision of current notions respecting the nature of the sun. Herschel's theory of a cool, dark, habitable globe, surrounded by and protected against the radiations of a luminous and heat-giving envelope, was shattered by the first dicta of spectrum analysis. Traces of it may be found for a few years subsequent to 1859, but they are obviously survivals from an earlier order of ideas doomed to speedy extinction. It needs only a moment's consideration of the meaning at last found for the Fraunhofer lines to see the incompatibility of the new facts with the old conceptions. They implied not only the presence near the sun as glowing vapours of bodies highly refractory to heat, but that these glowing vapours formed the relatively cool envelope of a still hotter internal mass. Kirchhoff accordingly included in his great memoir on the solar spectrum, read before the Berlin Academy of Sciences, July 11, 1861, an exposition of the views on the subject to which his memorable investigations had led him. They may be briefly summarized as follows. Since the body of the sun gives a continuous spectrum, it must be either solid or liquid, while the interruptions in its light prove it to be surrounded by a complex atmosphere of metallic vapours somewhat cooler than itself. Spots are simply clouds, due to local depressions of temperature, differing in no respect from terrestrial clouds, except as regards the kinds of matter composing them. These sun clouds take their origin in the zones of encounter between polar and equatorial currents in the solar atmosphere. This explanation was liable to all the objections urged against the cumulus theory on the one hand and the trade wind theory on the other. Setting aside its propounder, it was consistently upheld perhaps by no man eminent in science except Spörer, and his advocacy of it proved ineffective to secure its general adoption. Monsieur Faye of the Paris Academy of Sciences was the first to propose a coherent scheme of the solar constitution covering the whole range of new discovery. The fundamental ideas on the subject now in vogue here made their first connected appearance. Much indeed remained to be modified and corrected, but the transition was finally made from the old to the new order of thought. The essence of the change may be conveyed in a single sentence. The sun was thenceforth regarded not as a mere heated body, or still more remotely from the truth as a cool body unaccountably spun round with a cocoon of fire, but as a vast heat-radiating machine. The terrestrial analogy was abandoned in one more particular besides that of temperature. The solar system of circulation, instead of being adapted, like that of the earth, to the distribution of heat received from without, was seen to be directed towards the transportation towards the surface of the heat contained within. Polar and equatorial currents tending to a purely superficial equalization of temperature were replaced by vertical currents bringing up successive portions of the intensely heated interior mass, to contribute their share in turn to the radiation and to space, which might be called the proper function of a sun. Faye's views, which were communicated to the Academy of Sciences January 16, 1865, were avowedly based on the anomalous mode of solar rotation discovered by Carrington. This may be regarded either as an acceleration increasing from the poles to the equator, or as a retardation increasing from the equator to the poles, according to the rate of revolution we choose to assume for the unseen nucleus. Faye preferred to consider it a retardation produced by ascending currents continually left behind as the sphere widened in which the matter composing them was forced to travel. He further supposed that the depth from which these vertical currents rose, and consequently the amount of retardation effected by their ascent to the surface, became progressively greater as the poles were approached, owing to the considerable flattening of the spheroidal surface from which they started. But the adoption of this expedient has been shown to involve inadmissible consequences. The extreme internal mobility betrayed by Carrington's and Spörer's observations led to the inference that the matter composing the sun was mainly or wholly gaseous. This had already been suggested by Father Secchi a year earlier, and by Sir John Herschel in April 1864, but it first obtained general currency through Faye's more elaborate presentation. A physical basis was afforded for the view by Cagnard de la Tour's experiments in 1822, proving that under conditions of great heat and pressure the vaporous state was compatible with a very considerable density. The position was strengthened when Andrews showed in 1869 that above a fixed limit of temperature, varying for different bodies, true liquefaction is impossible, even though the pressure be so tremendous as to retain the gas within the same space that enclosed the liquid. The opinion that the mass of the sun is gaseous now commands a very general assent, although the gaseity admitted is of such a nature as to afford the consistence rather of honey or pitch than of the aeriform fluids with which we are familiar. On another important point, the course of subsequent thought was powerfully influenced by Faye's conclusions in 1865. Arago somewhat hastily inferred from experiments with the polariscope the wholly gaseous nature of the visible disk of the sun. Kirchhoff, on the contrary, believed erroneously, as we now know, that the brilliant continuous spectrum derived from it proved it to be a white-hot solid or liquid. Herschel and Secchi indicated a cloud-like structure as that which would best harmonize the whole of the evidence at command. The novelty introduced by Faye consisted in regarding the photosphere no longer as a defined surface in the mathematical sense, but as a limit to which, in the general fluid mass, ascending currents carry the physical or chemical phenomena of incandescence. Up-rushing floods of mixed vapours with strong affinities, say of calcium or sodium and oxygen, at last attain a region cool enough to permit their combination. A fine dust of solid or liquid compound particles, of lime or soda, for example, there collects into the photospheric clouds, and descending by its own weight in torrents of incandescent rain, is dissociated by the fierce heat below, and replaced by ascending and combining currents of similar constitution. This first attempt to assign the part played in cosmical physics by chemical affinities was marked by the importation into the theory of the sun of the now familiar phrase dissociation. It is indeed tolerably certain that no such combinations as those contemplated by Faye occur at the photospheric level, since the temperature there must be enormously higher than would be needed to reduce all metallic earths and oxides. But molecular changes of some kind, dependent perhaps in part upon electrical conditions, in part upon the effects of radiation into space, most likely replaced them. The conjecture was emitted by Dr. Johnstone Stoney in 1867 that the photospheric clouds are composed of carbon particles precipitated from their mounting vapour just where the temperature is lowered by expansion and radiation to the boiling point of that substance. But this view, though countenanced by Ångström and advocated by Hastings of Baltimore and other authorities, is open to grave objections. In Faye's theory, sunspots were regarded as simply breaks in the photospheric clouds, where the rising currents had strength to tear them asunder. It followed that they were regions of increased heat, regions, in fact, where the temperature was too high to permit the occurrence of the precipitations to which the photosphere is due. Their obscurity was attributed, as in Dr. Brester's more recent Théorie du Soleil, to deficiency of emissive power. Yet here the verdict of the spectroscope is adverse and irreversible. After every deduction, however, has been made, we still find that several ideas of permanent value were embodied in this comprehensive sketch of the solar constitution. The principal of these were: first, that the sun is a mainly gaseous body; secondly, that its stores of heat are rendered available at the surface by means of vertical convection currents, by the bodily transport, that is to say, of intensely hot matter upward and of comparatively cool matter downward; thirdly, that the photosphere is a surface of condensation, forming the limit set by the cold of space to this circulating process, and that a similar formation must attend at a certain stage the cooling of every cosmical body. To Warren de la Rue belongs the honour of having obtained the earliest results of substantial value in celestial photography. What had been done previously was interesting in the way of promise, but much could not be claimed for it as actual performance. Some pioneering experiments were made by Dr. J. W. Draper of New York in 1840, resulting in the production of a few moon pictures 1 inch in diameter, but slight encouragement was derived from them, either to himself or others. Bond of Cambridge, U.S., however, secured in 1850 with the Harvard 15-inch refractor that daguerreotype of the moon with which the career of extraterrestrial photography may be said to have formally opened. It was shown in London at the Great Exhibition of 1851 and determined the direction of de la Rue's efforts. Yet it did little more than prove the art to be a possible one. Warren de la Rue was born in Guernsey in 1815 and died in London April 19, 1889. Educated at the École Sainte-Barbe in Paris, he made a large fortune as a paper manufacturer in England, and thus amply and early provided the material supplies for his scientific campaign. Towards the end of 1853 he took some successful lunar photographs. They were remarkable as the first examples of the application to astronomical light painting of the collodion process invented by Archer in 1851, and also of the use of reflectors. De la Rue's was one of 13 inches constructed by himself for that kind of work. The absence of a driving apparatus was, however, very sensibly felt. The difficulty of moving the instrument by hand so as accurately to follow the moon's apparent motion being such as to cause the discontinuance of the experiments until 1857, when the want was supplied. De la Rue's new observatory, built in that year at Cranford, was expressly dedicated to celestial photography, and there he applied to the heavenly bodies the stereoscopic method of obtaining relief, and turned his attention to the delicate business of photographing the sun. A solar daguerreotype was taken at Paris, April 2, 1845, by Foucault and Fizeau, acting on a suggestion from Arago; but the attempt, though far from being unsuccessful, does not at that time seem to have been repeated. Its great difficulty consisted in the enormous light power of the object to be represented, rendering an inconceivably short period of exposure indispensable, under pain of getting completely burnt up plates. In 1857 de la Rue was commissioned by the Royal Society to construct an instrument specially adapted to the purpose for the Kew Observatory. The resulting photoheliograph may be described as a small telescope of 3½ inches aperture and 50 focus, with a plate holder at the eye end, guarded in front by a spring slide, the rapid movement of which across the field of view secured for the sensitive plate a virtually instantaneous exposure. By its means the first solar light pictures of real value were taken, and the autographic record of the solar condition recommended by Sir John Herschel was commenced and continued at Kew during 14 years, 1858 to 72. The work of photographing the sun is now carried on in every quarter of the globe, from Mauritius to Massachusetts, and the days are few indeed on which the self-betrayal of the camera can be evaded by our chief luminary. In the year 1883, the incorporation of Indian with Greenwich pictures afforded a record of the state of the solar surface on 340 days, and 364 were similarly provided for in 1897 and 1899. The conclusions arrived at by photographic means at Kew were communicated to the Royal Society in a series of papers drawn up jointly by de la Rue, Balfour Stewart, and Benjamin Lowry in 1865 and subsequent years. They influenced materially the progress of thought on the subject they were concerned with. End of Chapter 2, Part 1.